on quantum state preparation and optimized measurements, how we can perform quantum measurements for molecular simulations in an optimized fashion. I'll try to keep my talk in a high level and not go too much into the technical details, but I'll be happy to expand on some of the technical details if need be. So I'll start out with a brief pedagogical discussions on molecular simulations and how we perform molecular simulations. Um, and then I'll talk about a quantum algorithm for molecular simulations, specifically variational quantum eigensolver, VQE algorithm, and then we'll go into quantum state preparations. We'll talk about quantum optimal control theory, how we can bring this into the VQE framework. And then I'll talk about my own effort in advancing and addressing challenges in molecular simulations on quantum computers. I call this approach control VQE. And then we'll go into quantum measurements. We'll have some pedagogical discussions on quantum measurements briefly, and then we'll introduce randomized measurements and how we can improve such randomized measurements. So to start out with, let's forget about quantum computers. Let's just talk about classical computers, right? Let's say if there's an experimentalist chemist who synthesizes a molecule, a cool molecule, and comes up to a computational chemist or a theoretical chemist and say, well, I have this cool molecule that I synthesized. What can we do about it? It's almost certainly that a computational person is going to say, let's perform some calculations on these molecules and see what sort of quantum properties we can get. And what kind of calculations do we want to do? What sort of methods do we want to use to compute the properties of this quantum system? It really depends on whom you ask, actually. Most likely the person is going to say, oh, let's do some DFT calculations. And then there's this question about like what DFT functional do you want to use? But if you ask someone who works on wave function-based methods, they can say, well, how about we do a couple cluster calculations? How about we do DMRZ calculations? How about we do some CASPT2 calculations? There's a lot of methodologies that we can use to do molecular simulations on classical computers. There are many of this. And if you come to me, I'd most likely select one of these methods that I have developed so far. So it really depends on whom you ask, what sort of accuracy that you desire. There's many factors that goes into what sort of methodologies that we want to use. So there's been a lot of efforts in developing this method. So this does not just represent some acronyms, but there are efforts that has been invested over the last decades in advancing molecular simulations. Why do we do that? Why do we have so much of methodologies in quantum chemistry? That's because these methods can really rival with experiments. Wherever possible, it can reproduce almost exactly the experimental results that one would produce by performing experiments, which means that we can even replace these experiments if possible. They can dictate experiments. So instead of running experiments, say 100 experiments, trial and error, 100 experiments, we could perform the simulations and dictate the experiments and say, well, instead of 100 experiments, how about we run this 10 optimal set of experiments? And this is all because the application is really broad for such molecular simulations. We can perform drug design. We can design materials for energy storage and conversions, advanced energy storage and conversions, which is one of the challenges of modern science. We can even design or like aid in discovery of materials with exotic electronic properties. The only problem though is the computational scaling. All these methodologies that I have talked about, all these methodologies that I listed, all those acronyms, they scale rather bad, very rapidly with system size. As the molecular size increases, the computational cost also increases. This is a very nice plot that shows about the accuracy of these methodologies with the scaling. So the computational scaling goes from m to the third up to infinity, exponential scaling. These are the x-axis is just a molecular size. So the exact solution, which is the full CI, scales exponentially. So we can perform a few small molecules, but beyond that, it's just plain not possible. If we look into the DFT method, it scales entity tear. This is still quite good, but then we ask this question about like, well, do we trust the accuracy of DFT calculations? And there's a lot of approximations in DFT functionals that we also have to account into. If you go a little bit higher into this and say, well, how about a couple cluster calculations that they still scale pretty bad. And this plots over here illustrates how bad this goes. As the molecular size increases, we really quickly run out of steam. We cannot perform any more calculations for even for reasonably sized molecules with this highly accurate methodologies. And even if it's a small prefactor to the computational scaling, it still is bad. That it really quick out of steam. We talked about the time complexity, and there's this memory requirement as well, and that adds a whole new dimension into the computational requirement for such calculations. Quantum computers, on the other hand, has a potential promise that we can perform accurate simulations, exact simulations, without this curse of computational scaling on classical computers, without the heavy memory, without the huge memory requirements. It all started with this quote from Richard Feynman, where he talked about if you want to simulate quantum systems, then we might as well do it on a quantum simulator, right? Or as we might as well do it on a quantum system, the simulations, making it quantum mechanical. There has been a lot of efforts on developing quantum algorithms for molecular simulations on near-term quantum computers. These are a few representative of such an effort. I think my slide is a little bit outdated. There has been a lot of progress in the last few years about quantum advantage for molecular simulations, quantum advantage for chemistry. Again, this is all because um, if we are able to perform such accurate computation, almost exact computation for molecular simulations on quantum computers, this will aid in drug design, battery developments, energy applications, and materials discovery, as I mentioned before. Now, let's talk about how do we actually simulate a molecule on a quantum computer. So molecules are also quantum systems. They have a quantum state. Our quantum device or quantum computer is also a quantum system. So we have an initial state. We can apply a unitary, we can apply something onto the quantum computer, drive it to a target quantum state. And then what we can do is we can achieve a one-to-one mapping between the quantum state of the quantum device to the quantum state of the molecule, from which we can estimate properties of the quantum state, so molecular energies, other molecular properties as well. The unitary that I'm talking about here that we apply onto the quantum device to drive our quantum computer is a quantum circuit that comprises of a sequence of quantum gates. This is a quantum circuit, and I have a sequence of quantum gates over here. When we talk about quantum algorithms for molecular simulations, there's broadly two classifications. One is the quantum phase estimation algorithm, and these are more designed for the long term. This is more of a long-term solution. That's because it requires a full-scale fault-tolerant quantum computers, which we currently do not have. The current quantum devices are more prone to noise and error. We have limited coherence time, which means that we cannot implement an infinite circuit depth. So that is a huge limitation. BQE, variational quantum eigensolver, on the other hand, are more fit for near-term or current or near-term quantum devices. There's scope of introducing approximations in VQE in the VQE algorithm, and we can also adjust the circuit depth, which is a great fit for near-term quantum devices with a limited coherence time. So if we look into sort of the skeleton of a quantum computation for molecular simulation, we start out with some initial state on the quantum device, and then we have a state preparation piece. And I leave out some space for maybe furthermore computations or change of basis, and then we make measurements. So really speaking, the quantum state preparation piece and the measurement are two vital components in any quantum simulations. And today we'll talk about both of this. I'll talk about my own efforts in addressing challenges in quantum state preparation, as well as quantum measurements, and how we can advance molecular simulations by addressing these challenges. So we'll start out with quantum state preparation. To do that, let's look into what the VQE algorithm really entails. So VQE is a hybrid quantum classical algorithm. We have the quantum device where we prepare a quantum state, make measurements, and perform computations there. But we also use the capabilities of classical computers where we optimize over the circuit parameters. We'll see. So we started with our Hamiltonian, molecular Hamiltonian in the fermionic basis. We transformed this into qubit representation. So from the fermionic basis, the qubit representations, which are sum of tensor products of Pauli operators. We can do this via our favorite transformation techniques. There are Jordan-Wigner transformation, there's parity mapping, and there's Brabby-Kitev. So there are a couple of transformation techniques that we can choose from. And then what we do is we select an ansatz, which is in the form of a parameterized quantum circuit. So parameterized quantum circuits are quantum circuits with parameters which we can tune. And then on a quantum computer, what we do is we prepare a trial quantum state using our quantum circuit, and then make measurement of the expectation value of our molecular Hamiltonian, which is simply our molecular energy. So the problem with this state preparation is that our quantum circuit comprises of sequence of quantum gates, and we have to implement these quantum gates, each of these quantum gates, physically onto our quantum device. And then that is not achieved perfectly. So there's imperfection, there's noise, there's errors. And then another important factor here is the circuit depth. So for our quantum state preparation, we cannot accommodate infinite circuit depth. And so we're really limited by the decoherence time limit of our current and near-term quantum computers. And then we'll talk about this challenge in quantum measurements as well. So our molecular, as I mentioned before, our molecular Hamiltonian, we transform it from the fermionic basis into sum of products of Pauli. Do we measure each of these Hamiltonian terms, because that can grow really fast? We'll see more into that. But for the time being, let's assume that we prepare a quantum state and then we make measurements. So we measure the expectation value of our molecular Hamiltonian here. And then on a classical computer, what we do is we optimize over the circuit parameters. So remember that I talked about parameterized quantum circuit, where we have parameters that we can tune. So we can optimize this parameters so that our energy of our molecular energy minimizes, that we achieve a minimum, that we achieved an optimal energy over there. We can update the circuit parameters and go back, prepare a trial quantum state, make measurements, iterate until we call that our molecular energy sufficiently converges. And a variational algorithm guarantees that we'll always have the upper bound of the molecular energy. That is very useful and practical for current and near-term quantum computers. But then how do we actually implement a quantum circuit onto a quantum computer? So quantum circuits are more of an abstract level. How do we actually or physically implement this onto a quantum computer? So for that, let's look into how it works at a more hardware level. So at a hardware level, quantum computers are driven or controlled by analog control pulses. So any high-level quantum algorithm has to be compiled down into low-level control pulses, starting with a parameterized quantum circuit. We have to compile that to analog control pulses, and then we drive our qubits or quantum computers using the analog control pulses. So how that works is actually rather simple. So each of these gates in the quantum circuit has a predefined control pulses. All we have to do is to look up the control pulse that corresponds to each of these gates in our gate sequence, concatenate them, combine them, and then form a set of control pulses and simply drive our qubit. That's really simple. So that's the gate-based compilation, which is very fast because it only amounts to looking up what is the corresponding control pulses for our gates. And now the problem is that the pulse corresponds to each of these gates in the quantum circuit And the set of gates that we form by concatenation is not global for the entire circuit, right? Because we're just looking up for each of this gate, what is the corresponding pulse, and then simply concatenating them. So they're not really optimal. The gate duration, the simulation duration, the circuit depth, really depend on the number of gates in the quantum circuit. And this can be unnecessarily long because it's not really optimized. And that and since we have just been concatenating this pulse for each of these gates. Just to give an example over here, if we want to implement a CNOT gate, it takes about like 500 nanoseconds in this IBM-Q device. And if we have some of this, a couple of this, it really quickly, the circuit depth, the gate duration quickly increases, and then we approaches the decoherence time limit of our near-term quantum devices rather quickly. One of the questions that we ask at this point is that, is there an optimal pulse that drives our qubit, rather than concatenating the pulse from each of these gates? Is there an optimal pulse that we can use um, for such simulations? And that's exactly the question that we asked some time ago. And to answer this, let's look into what's quantum optimal control theory, um, where the aim is to um, design or optimize control pulses to drive a quantum system, right? So it works by minimizing a control objective function. This is a very nice illustration that demonstrates how quantum optimal control theory really works. So we start out with a pulse, some pulse shape over here in this plot, and we measure the fidelity. We have about 70% fidelity here. And then we optimize this pulse shape somehow, and at each of this iteration, the fidelity increases, going from 70 to 79. And then finally, we have about like 99% fidelity with an optimal pulse shape. What we can do is we can bring in this quantum optimal control theory as a routine in the various node quantum eigensolver algorithm. And then instead of instead of using quantum circuit, instead of using this abstract level quantum circuit, what we can do is we can use the control pulses directly into the VQE framework. So what we do is we define the objective function in the quantum optimal control routine as the expectation value for molecular Hamiltonian. And then we use control pulses instead of quantum circuit in the optimization. And then we variationally optimize the pulse shapes. We'll look into that. And then hopefully we'll drive from the initial state, the Hartree-Fock state, to the full CI solution, so the exact solution for our molecules. And then we can measure our molecular energies. So let's look into how this really turns out. We call this the control VQE algorithm. Similarly to the conventional VQE algorithm, we start out with encoding our molecular Hamiltonian from the fermionic basis of the qubit representation. And then now we define a pulse shape. So this could be square pulses, this could be Gaussian pulses, or flat top Gaussian pulses, any pulse shape that can be physically implemented onto our quantum device. And then we initialize the pulse parameters. So the pulse parameters are amplitudes, frequencies, pulse time even. And so far, what I have found is that initializing with such random numbers works well. We don't have to invent certain complicated techniques for the initialization. Maybe it helps, but for now, let's stick into random initialization. Then onto a classical computer, we implement this control pulses. So rather than implementing an abstract level quantum circuit, we implement the hardware level analog control pulses. And then we make a measurement for the expectation value for molecular Hamiltonian, which is the molecular energy. And then on a classical device, on our classical computers, we optimize over this pulse parameters. So we optimize over the amplitudes, the frequencies, and time segments and other things. And then we update this pulse parameters. And then using this newly optimized pulse, we drive our qubit again, make measurements, and we come back, optimize these pulse parameters. And so we iterate this process until the molecular energy is sufficiently converts. And again, because of the variational algorithm, it will always result in the upper bound of the molecular energy. Now, what I've done is I've simulated our control VQE framework and on transmon qubits. So by time evolving transmon qubit with simple square pulses. So this is the pulse shape that we have taken. It's a simple square pulse. It has only two time windows. So the parameters or the pulse parameters are really just the amplitudes, frequency, and the switching time over here. And this is a simulation done on 2 qubits for 2 diatomic molecules, as we'll see. The total pulse parameters here enter as a hyperparameter into optimizations. And I'll just note that we have analytical gradients for this the pulse parameters. And so the computation, the numerical experiments can be rather fast and easily parallelized. So let's look into some numerical results here. So these are the dissociation curve of hydrogen molecule and helium halide produced with our control VQE algorithm. So as this shows the energy of hydrogen molecule and helium halide as the molecule dissociates, right? These are two interesting systems. What I've shown here is the Hartree-Fock energy, which does not contain any electron correlation. And our reference full CI, which is the exact solution, which contains the electron correlation on top of the Hartree-Fock solution, and then results from our control VQE framework. One thing that you notice here is that for the hydrogen molecule, as the bond dissociates, Hartree-Fock energy without the electron correlation deviates off from the exact solution. Whereas for the helium halide ion, the Hartree-Fock solution becomes equivalent to the exact full CI solution. This is because for the hydrogen molecule, as the bond dissociates, static correlation starts to dominate. For helium halide ion, it's the dynamic correlation that stabilizes this molecule. But one thing that you notice over here is that control VQE exactly reproduces our full CI curve, so the exact solutions. So with our control VQE framework, we can get the exact solution. Now let's look into the pulse durations, the pulse durations that's used for the simulations. At around the equilibrium, it's about 9-10 nanoseconds. And then as the bond dissociates, for hydrogen molecule, the pulse duration increases and then sort of plateaus. Whereas for the helium halide ion, the pulse duration decreases and it's almost as if we do not need to drive for qubits anymore. And that's really because for hydrogen molecule, it's the static correlation, it's the static electron correlation that dominates as you dissociate the bond. And for helium halide ion, you do not need this electron correlation. You don't need the electron. You do need some electron correlation, but the energy really is equivalent to the Hartree-Fock solution. So this means that the pulse duration that we get from our control VQE framework reflects the effect of electron correlation. So this is something physical. If we compare our pulse duration to gate-based compilation, to gate-based ansatz that we talked about, remember that when we talked about conventional VQE simulations, we said, oh, we're going to choose some ansatz and parameterize quantum circuits. So we've taken two ansatz, RY ansatz and UCCSD ansatz. UCCSD ansatz is a popular ansatz in the VQE framework. And we compare the duration for these two diatomic molecules, hydrogen molecule mapped onto 2-qubit as we have seen before. Lithium hydride, we mapped this onto 4-qubit. The pulse duration you can see are quite different from the conventional gate-based ansatz to the controlled pulse optimizations that we have been doing. For lithium hydride ion, this differs by the pulse duration decreases rather dramatically, 15 nanoseconds to about 82,000 nanoseconds for the UCSSD ansatz. It's quickly approaching the decoherence time limits for these quantum systems. So another question that we can ask here at this point is that, well, I said we're gonna use a simple square pulse with 2 time windows, but how do we choose that 2 time windows? That's an interesting question. We do not want to over parameterize or under parameterize our pulse so that the variational flexibility is there. What we can do is we introduce what's called the adaptive pulse parameterization. So I can illustrate, I can explain this with this very nice illustration over here. So what we do is we start out with a constant amplitude pulse, square pulse. So this does not have any time windows. It's just a straight. It's just a constant amplitude with that we drive our qubits with. We perform or control VQE optimization, and then in the next step, we sort of divide our pulse into two time windows. So we divide it over here randomly. Then we have a two time window square pulse, and then perform VQE simulation. And then in the next step, we again divide this into three time window square pulses and so on. So we can keep on dividing, and then we can measure the energy. We can get the energy out from our VQE framework, and then check if that energy is really converged or not. So if we look into this, what's shown here is the energy error compared to the full CI solution, the reference that we have. And then on the x-axis is the number of time windows. So for hydrogen molecule and for helium halide ion, the number of the number of time windows that we need is only about 2. So as we approach 2, it sort of easily like converges. So the molecular energy converges with just 2 time window square pulses. For lithium hydride ion, we have about, say, 5, it's almost converts, and then 6, it's converts over here. And the shaded pink region over here is the chemical accuracy that we desire. So this is the energy error, and with about 3 time window square pulses for lithium hydride ion as well, we have it. We have chemical accuracy over here. So this is one way to sort of restrict our pulse so that we do not over parameterize or under parameterize our pulse in the VQE optimization. I have this implemented in this very nice user-friendly control Q framework, which is available on our GitHub. So do check it out. It's a Python C++ code, and you can easily parallelize this to run on your HPC solutions. So with that, let's move into the quantum measurement part. So we'll talk more about quantum measurement in the VQE framework. If we look back into the VQE algorithm, we said we're going to measure the expectation value of our molecular Hamiltonian. So we'll discuss the challenges and sort of opportunities here and talk about my own effort in optimizing this quantum measurements. So remember to look into how do we actually perform this measurement. Remember that we transform from the fermionic representation to the qubit representations, which is simply just sum of tensor products of Pauli operators over here. So this is a concrete example over here. Our Hamiltonian has 7 Hamiltonian terms. I have removed the tensor product notation and represent the tensor products of Paulis as Pauli strings. And this is, excuse me. And this is the notation that I'll use throughout the remainder part of my talk. So this is a concrete example of a Hamiltonian transform into a qubit representation. And if we have to perform measurements, we have to measure each of these Hamiltonian terms separately. So yeah, we have to measure each of these Hamiltonian terms separately. The problem here is that if you want to these Hamiltonian terms, we have to repeat the state preparation for each of these measurements to repeat the quantum state preparation in the VQE framework, which means that there's scope for errors to accumulate from the state preparation. And then frequent measurement also means that there's scope for errors that can accumulate rather quickly from errors stemming from the measurements. And our goal here is to reduce the number of measurements. We want to reduce the number of measurements so that the error accumulation decreases and we can increase the accuracy of our VQE framework. We usually perform quantum measurements in the computational G basis, the standard computational basis. So we perform a measurement and we get a reading 0 or 1. We can also transform the other Pauli strings, so Pauli X and Pauli Y, into the standard computational basis and make measurements. So for example, if we have a Pauli X, we can just simply implement a Hadamard gate and then make measurement in a computational basis. And another interesting feature or an important feature here is that poly strings or Hamiltonian terms that mutually commute with each other, or group of poly terms, or a group of poly string that mutually commute with each other, can be simultaneously measured instead of measuring them separately. So if we look into my Hamiltonian example here, the first four terms mutually commute with each other, and the remaining three terms mutually commute with each other. So this means that we can perform simultaneous measurements for the first four and simultaneous measurements for the remainder three. So we just get away with two measurements instead of measuring them separately. So that's reduced from 7 measurements to just 2 measurements. Quite a reduction. Again, we still have to sample our measurements because quantum measurements are not deterministic. And so we have to sample to estimate up to some error threshold over here. There has been this has been the focus of a lot of work in partitioning the Hamiltonian terms, um, mapping our polystrings or Hamiltonian terms into graphs, and then finding minimal click, sort of like to optimize, sort of exploiting heuristic optimization techniques to partition the molecular Hamiltonian so that we can reduce the number of measurements to make. It has been the focus of this works over here. We're not going to go into details about this works, but I just want to show a visual representation of how this grouping really works. So what I've done is I've represented my Hamiltonian terms. So these are all Hamiltonian terms in graphs. So the nodes over here are our polystring, tensor products of our poly operators, and a connected line means that they mutually commute with each other. So they commute with each other. And then this is Hamiltonian for hydrogen molecule with about 180 Hamiltonian terms, or 185 poly strings. And using such optimization techniques that I've talked about, I think I used a Monte Carlo simulation for this, just to achieve such grouping of mutually commuting poly strings or Hamiltonian terms. So you can see that we can group this into cliques. It's called cliques when you group the nodes and the edges together and sort of like partition it over here. And you can see that you can group this Hamiltonian terms. So all these groups over here are something that we can simultaneously measure. So instead of individually measuring 185, we can simply measure the number of groups in this polystring. So this is one way we can reduce the number of measurements to make. An alternate is the classical stellar tomography. What it really entails is that we perform, so let's say we have a quantum state, so our quantum device, let's say we prepared some quantum state, and then we can perform randomized measurements. So we can randomly rotate our quantum state and then make randomized measurements. Using the outcome from such a randomized measurements, what we can do is we can construct or estimate properties of our quantum state. For example, the molecular energy and the expectation value of our molecular Hamiltonian that enters into the VQE framework, right? So we perform this random measurements, store the measurement outputs, and we look into our Hamiltonian terms Hamiltonian terms of a molecular Hamiltonian, and then using this randomized measurement outcomes, we can construct the molecular energy. The nice thing about classical stellar tomography is that, let's say if I have about L Hamiltonian terms or L polystrings that I want to measure, we can simply get away with order of log L random measurements to estimate the expectation value of all of this L polystrings or Hamiltonian. That's quite a fantastic reduction in order of log L. This illustration shows how we actually perform such type of measurements. So in this lower block over here is my Hamiltonian term, so the polystrings that I'm interested in estimating the expectation value of our expectation value. So let's say these are 3 polystrings components of our molecular Hamiltonians. What I do is I do not measure these Hamiltonian terms, but I measure some random polybases. So I select randomly polybasis 1 and polybasis 2, and then I make measurements for this random polybasis. And then using the measurement outcome from such a randomized measurement, we can construct the expectation value of our poly observables here in the lower block. Let's see how that goes. So if we look into the first poly observable, the first component, you see that it commutes with poly basis 1. It's easy to tell by simply looking at the qubit position over here. You can see that y, this is poly y, this is poly y over here. They're equivalent. It's the same for this over here as well as for this over here. So this commutes with the first poly observable, which means that we can use the measurement outcome from poly basis 1 to construct the expectation value of our poly observable 1 over here, the first Hamiltonian term. Similarly, if we look into the second term, this commutes with poly basis 2, and so we can use the measurement outcome from poly basis 2 to estimate or construct the expectation value of this. And then for my third term over here, you see that it commutes with both of these poly bases. So we can use the measurement outcome from both of this to estimate the expectation value of my third term over here, which means that I already have a reputation. Reputation is required to achieve accuracy of a certain threshold. So by performing just 2 measurements, I've measured the expectation value of 3 poly observables with 1 already repeated, instead of measuring them separately. So would be if we were to measure them separately, then we'd be performing 3 measurements. But we performed just 2 measurements and then got the expectation value with 1 already repeated. This is quite nice. Now, the problem with, while this is very nice, the problem with classical stellar tomography is that the order still scales in the order of log L, but there's a prefactor. So number of measurement required scales with order of log L, and we have to sample to get up to some error threshold. But there is a prefactor that depends on the weight of the poly strings of our Hamiltonian terms over here. So the weight is simply the number of poly operators into the Hamiltonian term. So if we look over here, this is a weight of 1. Here, this is a weight of 3. This is a full weight poly operator, is a weight of 5. So this can easily grow. The number of measurement can easily grow if our Hamiltonian terms are non-local, which means if I have many full weight Hamiltonian terms into a molecular Hamiltonian, then the number of measurements that we need would exponentially scale, right? Okay, so just to give an example over here. So these are my randomized measurement, and this is the Hamiltonian term that I want to measure, right? So I have a full weight Hamiltonian term that I want to construct the expectation value from these 2 randomized measurements. You see that this Hamiltonian term does not commute with any of these randomized measurements. So the randomized measurements are simply useless in this case. We cannot get the expectation values of our Hamiltonian over here because they don't commute. Now, this is the case for almost all of our molecule. If we look into the Hamiltonian terms of, say, this uracil molecule, which is about 2.5 million Hamiltonian terms, or 2.5 million poly strings, shown over here is the corresponding weight for many poly strings. So these are the number of poly operators that has this many weight in my 2.5 Hamiltonian terms for this uracil molecule. And we see that there are many Hamiltonian terms that has very high weight. So if we were to perform the classical stellar tomography, we'd end up requiring many measurements than if we were to measure them, if we were to measure the molecular Hamiltonians separately. So what can we do? What we thought about is, instead of targeting measuring the expectation value, so targeting to estimate the expectation value of our Hamiltonian terms, which is full weight Hamiltonian term, what we can do is we can partition our poly observables, such as this. It's a very naive way of partitioning, and it's probably not going to work, but we'll see. If we partition this, what we see here is that, for example, if I take the subpartition over here, this commutes with my randomized measurements, my first randomized measurement. And this one commutes with my second randomized measurements, and that commutes here as well. And this one also commutes over here. These are all handpicked just to illustrate how this really works. What it really means is that if we partition our poly observable or Hamiltonian terms, we can still use this randomized measurement protocol and construct the expectation values meaningfully. And what we have done is we have used what's called the cumulant expansion in statistics to expand our Hamiltonian terms into sum of products of polystring that contains very few weights. So I've denoted my poly operators by the letters A, B, C, D over here, and I'm interested in estimating the expectation value of this Hamiltonian term over here. And what I've done is use the cumulant expansion to expand this as sum of a sum of um, polystrings, a sum of products of polystrings that contains fewer number of weight. And this is going to remove the identities over here, and this is going to use the shorthand notation, but it does preserve the qubit indices. So if you look into the first term in this expansion, it only has a weight of 1. So the randomized protocol would be much favorable. If you look into the second terms over here, the maximum weight a polystring or a Hamiltonian term have is just 2. And so this would be still be very favorable for the randomized measurement. And then what we can do is we can control this truncation. We can truncate up to say the first order expansion in the cumulant, first order in the cumulant expansion, second order in the cumulant expansion, or up to say we can go up to 3 order in the cumulant expansion. Just to show you what this cumulants really are. They're simply nothing but just, again, sums of products of polystrings that contains fewer number of weights again. So I have this partitioning scheme, and I again have to construct the cumulants for the cumulants in this expansion again over here using such a definition. And we can, again, the nice thing about this is that we can control how much we want to truncate and what's the accuracy desired and so on. Now, just to give a concrete example, I have a Hamiltonian term, which is poly X identity, poly Z and Y over here, and I form such a partitioning in terms of cumulant expansion, so that we can measure the expectation value of each of these terms from the randomized protocol. So how it really works is I have some random measurements, and this is the poly observable that I'm interested in. If I do not expand this, they don't commute, and so we cannot use the results from the randomized measurements. But if we expand this in terms of cumulant expansion, so these are the terms that appears in the cumulant expansion, each of this term commutes with my randomized measurements, either the first randomized measurement or the second randomized measurement. And now we can get the expectation value of this poly observable here. We can construct this by simply summing them all up, collecting the expectation values, and then summing them up, and we can construct the expectation value of our poly observable that we are interested in here. So this will be very useful for molecular Hamiltonians with a very high weight Hamiltonian terms, which is usually the case. So if we look into the sort of the algorithm over here, what we do is we perform some randomized measurement, store the measurement outcomes, and then expand our Hamiltonian terms in terms of sums of products of polystrings that contains fewer number of weights. And then we compute each of these components in the cumulant expansion. We collect the expectation value of these components, sum them all together following this cumulant expansion scheme, and get the expectation value of our molecular measurements. So we can still use the randomized measurement protocol here. I've implemented this again in this high-performance multi-threaded competing library called QMIAS. It's again available on my GitHub, so do check it out. It has very user-friendly capabilities to perform all of these quantum measurements. If you have measurement outcomes, you can use your cumulant expansion scheme to construct expectation value of not just molecular Hamiltonians, but any Hamiltonians with high weight polystrings and very lengthy polys. These are some numerical results. So what I've shown here is what I'm showing here is the errors in the molecular energy for these two molecules, beryllium hydride and ammonia, which is mapped onto 12 qubit and 14 qubit. It has this many number of polystrings in the Hamiltonian term. The purple curve over here shows the result from just using randomized measurements from the classical stereo tomography. The green curve over here is from our cumulant expansion scheme. And the x-axis is simply the number of random measurements that we take. So we can just think about choosing 100 random measurements and constructing expectation value of all of my molecular Hamiltonian, which results in a little larger error over here. Or we can choose about 10,000 um, randomized measurements, and then from that outcome, we can construct the expectation value of our molecular Hamiltonian, and then we get very high accuracy. One thing that you notice over here in both of these cases is that we just using the classical serial tomography, the molecular energy does not really converge at this limit, at this number of measurements that we take over here. It's still sort of like jumps up and down over here, and it's really not very conversing. Whereas with our cumulant expansion scheme, you can see that it's clearly converging with in this range of the number of measurements that we can make. And that's again limited on our current and near-term quantum devices, because we cannot perform infinite number of measurements. It's really limited. You only have like a fewer quota of measurements that you can make in, say, for example, the IBM-Q devices. And so with our cumulant expansion scheme, just with fewer number of measurements, we can improve the randomized measurement protocols over here. And then I scale this up to 16 qubit. Similar story over here, the randomized protocol. Even if I increase the number of random bases, the number of random measurements, it still does not converge. It's still oscillating a little bit. Whereas for the classical serial tomography, whereas for the cumulant expansion, excuse me, for the cumulant expansion, it's converging. And another thing is the shaded region is the standard error of the mean. And so you can see that for randomized measurement, the error is rather large. It's still not converging at all anywhere. Whereas for the cumulant expansion scheme, you can see that our errors are rather small throughout this curve over here. So that's quite an advantage. So far, we've talked about, let's say, quantum state preparation in the VQU framework, or how we can optimize the simulation time or the gate duration. We talked about quantum measurements, how we can reduce the number of measurements to make in order of log L. We have seen some nice visual representation of how we can group the Pauli strings therein. But for molecule, really, another axis of challenge or other problem is the number of qubits that require for simulating molecules. So what I'm showing here is the number of qubit requirements for these alkane chains. So these are simply just propane has 3 carbon atoms, butane has 4 carbon atoms. I just increase this increase the number of carbon atoms up to octane, and you can see that when we reach about like the 7 carbon atoms up to heptane, we already require a little more than 100 qubits. So how do we address this challenge? Because we have limited number of qubits, and we cannot accommodate infinite number of qubits. Even then, the number of qubits requirement for our molecular system still grows. One way to tackle this is to divide the molecular system into subpartitions, and then use these subpartitions and simulate the subpartitions onto a quantum computer. That way, the number of qubits reduced, because the subpartition that we want to target would always be smaller, would always contain smaller number of atoms. And that has been the focus of my work in collaboration with Professor Ike Chuang here at MIT, as well as with our collaborators at ETH Zurich and University of Copenhagen. We just had this paper out very recently in, I think, PRX Live. So I'm just going to highlight my work over here and not really go into any details therein. With that, I think I have come to the, okay. Before coming to the end of my talk, this embedding techniques, this subpartitioning technique that I'm talking about over here, all these efforts are available on my GitHub in this QM package that's on my GitHub. This is very user-friendly, and not only you can use this for molecular simulations on quantum computers, but you can use this to simulate molecules, solids, using classical computers, using our normal computers for high-level quantum chemistry methodologies. So do check it out. I think this would be very useful if you are if you want to simulate some molecules, some very large molecules or some solids, maybe 2D materials and other things. With that, I've come to the end of my talk. I want to thank people that I've worked with, Van Voor's group here at MIT, Mehal's group at Virginia Tech, and my collaborators at MIT, ETH Zurich, Virginia Tech, and at Rigetti. And I want to thank you all for your kind attention. I'd be happy to answer any question.
Thank you, Dr. Romesh. We are now open for questions and answers. I think there are no further
Hello.
questions.
Hi, sorry. So in your plot regarding that scaling with respect to the shadow and the cumulant one, so the error bars, right? What are those error bars? And
so these are just the mean of the standard error, standard mean
so
error.
yeah, so somehow they don't. It's not connected with the number of random basis elements because it seems to be constant, more or less.
It does. In principle, it should be related to the number of random measurements over here. You'd expect for classical pseudo tomography that if you increase the number of random measurements, this error should reduce, right? Because you're accumulating a lot of measurement outcomes, and then the probability of hitting your Hamiltonian elements simply increases. But I think for classical pseudo tomography, we haven't really reached that limit yet. So it's not up to, like, say, for example, if I go to this smaller molecule over here, it's not up to like 10,000. We still have to go up to like, I think, 1,000,000 terms over here so that the error bar would increases. Whereas for the cumulant expansion scheme, you see that it does fluctuate a little bit over here, here and there, but rather they're, I think, like pretty good. Here you see like slight. I think that it's not very visible over here because I've taken the
Maybe
standard
just the
error.
last one. There's a small squeeze from
Yeah,
5,000 to 7,000.
yeah. It's not really constant. In principle, it should decrease, but we still would require a lot more measurement in the classical pseudo tomography protocol.
Thank you.
Thank you.
Okay, it seems there are no further questions. So let us thank Dr. Romesh once again. So we have come to the end of today's evening session. We once again thank our speakers, Dr. Augustine Katrimayum, Dr. Vishal Mairangam, and Dr. Oinam Romesh Meitei. So we'll wind up today. Thank you all. Thank you all the participants.